why not to play with them? Especially the E61 is quite nice because it's a very, very widely spread phone. Of course, for all the hardcore users, they don't use the phone anymore for, I guess, 2 years or so. But yeah, they're good to play and experiment with. So the big question when I started was, okay, didn't really anybody play with Symbian OS security and publish anything? And I really wondered why they didn't. So for one thing, that's for sure, is because everything is like in those funky C++ style stuff. You have buffer sizes and bounds checking everywhere. Everything is in Unicode. So if you're not that experienced with security, reverse engineering, shell coding, and all the stuff, it's not fun to start with. So yeah, why the other reason why people should have or could have looked at it is because you have all this the funky stuff like MMS, Symbian syncing, many third-party applications. There's really a lot to break out there, and it's just widespread. So, and now, okay, now we have pips and OpenC, which are very new. So, yeah, that's why we're going to look at it now. And as I said before, Nokia just ported Qt to the platform. But I will not cover it. But so if, yeah, that's another standard library that yeah, could possibly invite people to take a deeper look. So buffer overflows on Symbian OS. Yeah. The older devices, about maybe from a year back, which all run on the mostly on the ARM version 5 cores. These don't support non-executable stack. There is no stack canary use in the compilers. So yeah, basic thing: you overwrite the return address on the stack and hijack the program counter and execute your own code. Very basic. Yeah. On newer devices which run on the ARM version 6 cores, they actually have non-executable memory implemented. And yeah, it's not that it's implemented. I tried it, and yeah, you just get a code abort exception, and yeah, so just simple stack overflow attacks won't work on your devices. You of course still should be able to do like return to libc or other libraries and other more advanced techniques, but I haven't tried that. That's just for other people to do. Why I still think this is it's still relevant, because there are many devices out there which just have ARM version 5 cores, and so Symbian OS only supports non-executable memory if the CPU actually supports it. So yeah, that's the thing. So now, each Symbian OS application of course, has virtual memory. The memory mapping looks like that. Yeah. So you basically always have your stack at this address. Of course, you have some slight offset because there's always some initial data in the beginning. The heap is usually at this address, so that's pretty fixed. So there's no randomization or nothing. It's so if you debug and find the buffer addresses in your application on the stack, then they're there. The other nice thing about ARM CPUs is the byte order. So because in shellcode you don't want to have zeros in your strings, which you use for say attacks against string copy. So you can just leave out the leading 0, and because string copy will just add it back later. Of course, this is a very specific case, but it's a nice thing. Yeah. So before we actually get to show you some shell coding, just a very quick overview of the ARM processor. So that's of course very common. As far as I know, Symbian only supports the ARM CPU. Of course, you can cross-compile it for the desktop for emulation. ARM has this thing that you have different caches for data and instructions. So you always have some problem with self-modifying code. I will, show you some stuff later. Yeah. Other nice thing is you have conditional code execution, so you can like write really tiny shell code and avoid a lot of zeros, which you always don't want. So yeah, I never actually ever used compare in any of my things. So, oops, sorry. Yeah. So yeah, you have a potential for zeros in ARM if you write ARM shellcode, so you want to avoid that. The program counter and stack pointer are just registers, so you can just read them, so you can very easily determine where your shellcode ends up on the stack. You don't have knobs, so you just build your own, just copy a register onto itself, so you change the processor state and yeah, do nothing. So, yeah, just as a reminder, I won't like explain the shellcode stuff too much because it's not that interesting. The slides are for download, so yeah, this is very simple part. We just call printf and sleep. Yeah, so just a visual example. I will show you the details of shell coding in a bit. So if you're familiar to operating systems, you know, like Linux and many, in the Unix operating system, normally they have the whole, most of the interface to the system with system calls, which are very nice for exploitation, because calling system calls doesn't require knowing anything about DLLs. You don't have to load DLLs and stuff, but in Symbian, the system interface works by DLL calls. So you either have to use DLL, use function calls which are stored in the basic or in the system interface DLL, the e-user DLL. Or you have to load other libraries. For most stuff, you actually can just use the stuff in e-user DLL. The nice thing here is, on a specific device, a function will be always mapped at the same address, so you don't need big function lookup stuff, function lookup code, and so on. Of course, if you use stuff, if you use function from other libraries, you will always need to look them up. Of course, there are other libraries which also are at the same address, but that's normally not the case. So I started to check out which of my devices had like the same OS version, and really the same OS version is not just the same number, but the same build number. So to see if we can, how easy it is to write actually really portable exploitation code. And I saw that it's always, I never found two device types which actually have the same mapping. Still, the offsets from some, still the libraries are really the same. You can see just two functions, the difference, the address difference between two function calls are the same, but they're just mapped at another address. So that doesn't bias too much. It's just, so I wrote a small utility which will hopefully put on the website, which just dumps all the stuff. So if you have Symbian device, you can just dump it out. Maybe, yeah, you find something interesting, but yeah, just for. So since we're going to need function addresses to actually call functions, we need to look them up. Because if you want to do more advanced stuff other than printf, you're going to need other libraries. And yeah, in Symbian, you actually look up functions not by a function name, but just a number. And so for exploitation, this is quite nice because instead of having big strings in your exploit, you just have small numbers and you just look them up. The pain, of course, is what number is what function, but yeah, IDA Pro knows Symbian binary, so you can just like open a binary and we'll just show you, okay, this function that has this ordinal and it's in this library. Bang, you have everything. So, yeah. Since we're going to need library loading code, I wrote a very small, compact piece of code. 276 bytes, which of course if you come from the PC world that's already a big part of an exploit, but the Symbian stuff actually gets quite big because you will basically write your stuff in C++ and will going to disassemble that and reuse that. Just another example, on the left side is the C code, on the right side is part of the assembly code, not too interesting, I already covered that. So as I said earlier, you have to, of course, always avoid zero stuff and other special characters. If you want to go to string functions, well known from all other platforms. In this case, I just changed my old 0-free decoder from Windows CE and just added another 32-bit value to just encode more bigger payloads, because you cannot just XOR your payload anymore against just one 32-bit value. If you have a certain size, you will always change something to 0 or some other value you don't want. So just 2 keys and nothing really fancy. Code will be hopefully online. Yeah. The other thing, instruction cache. That's a common problem. Or if you exploit ARM devices, because you need to decode your shellcode, you will have self-modifying code. And in the beginning, the shellcode ends up on the stack. So if you start executing on the stack will be cached. The stack is then cached in the instruction cache. And the encrypted part is cached as encrypted. So if you start decoding the payload, the decoded version will only end up in the data cache. So you have to somehow either flush the data cache or move the shellcode to some position that's not already cached in the instruction cache. So I mostly try to just move decode the shellcode to some other part of the stack. But if you have a bigger shellcode, it sometimes is necessary that you just allocate some memory on the heap and just move it there, and then it's 100% that memory is not in the instruction cache and everything works fine. I have a lot of slides, so I'm going to skip these 2 things. So Symbian, the Symbian operating system